Um, yeah, good morning, everyone. I'm going to give you a 15 minutes lesson in your week 3 of wave and optics and oscillations. So today we are going to talk about something funny, and we are going to take the ideas you already know from physics 3, oscillations, waves, amplitudes, superposition, interference, and use them to understand a modern physics idea, quantum superposition. The goal is not to memorize this any jargon about quantum computing, but the goal is to build a bridge from wave reasoning to qubit reasoning. And by the end of this short lesson, you should be able to explain two things. First, what is the difference between wave superposition and quantum superposition? And second, what is a Hadamard gate and how is it compared to a classical wave being split? So let's start with something familiar with you from week 1 of physics 3. So first question, in a wave diagram, what does the amplitude represent? Yes, the amplitude is the height or the strength of the wave. If I draw a taller wave, I mean a stronger wave. I mean a larger amplitude or the higher wave. This is physics, something physical. Now imagine two waves are overlapping with each other. I imagine two waves overlapping with each other. Take 5 seconds and tell me about maybe what will they do to each other. Yes, their peak will end up with each other, and then the two peaks will become taller. Now imagine a peak mixed with a trough of a wave. What will they do? Yeah, they will cancel with each other. So the first one is called constructive interference, and the second is called destructive interference. So the key physics 3 idea is this: wave do not just exist separately. When they meet each other, when they overlap, they combine with each other. Sometimes the result is larger, and sometimes the result is smaller. So in case they are larger, it's called constructive interference, and in case they are smaller, it's called destructive interference. So let me ask you a quick question. If I only know one individual wave, I know their amplitude in absolute number, um, and I also know the other wave amplitude. And when they meet each other, do I know perfectly whether they will end up with each other or they will cancel with each other? Yes, we cannot know it because we know their amplitude, but we do not know their phase. So there's no way we can know whether it's, for example, positive or negative, and also when so there's no way we will know whether they will lie with each other or whether they will know whether they will cancel with each other. Now move on to the quantum side. And a classical bit is very simple. It is either 0 or 1. Qubit is something different. Qubit is something superposition between alpha 0 and beta 1. So for today's introductory version, we will treat alpha and beta as real amplitudes. However, in real case, they can be complex number. So alpha and 0 means something about measurement. Alpha square and beta square are the probability of measuring qubit 0 and qubit 1. And of course, they will add up to 1 because they're denoting the probability of something. So for example, alpha square can be 0.5 and beta square can be 0.5. So what is the square root of 0.5? Can anyone tell me? Yeah, that is a very complicated number, right? So, but we can do something simpler. We can write as square root 1 over 2. So that will be something cleaner that we will use this notation for many times, even for this 10 minutes lesson. So there is one important difference from the classical wave diagram. First of all, the cubic wave diagram, alpha and zero, they cannot be enormous. They can only be smaller than one because they have to add up to one, and they cannot be arbitrary. And if alpha is large, beta have to be has also to be small as well. So let me ask you a quick question: if alpha equal to one and beta equals zero, what is the probability of measuring cubic zero? Yeah, we will measure zero with probability one. And if alpha equal to 1 over third 2 and beta equal to 1 over third 2, what are the probabilities of measuring either of the state? Yes, is one half all the time, because 1 over third 2 we square it to 1 half. So let's connect this back to optics. We have this notation, something complicated, but just maybe memorize it for now. We'll turn to something called the Hadamard gate, when we pass a cubic zero into it. And I'm going to show you exactly that. It's like splitting a linear beam into two different directions. Something called the beam splitter that you already know in week 2. So let's connect this back to classical optics. In optics, the optical spin splitter, as you know, takes one incoming beam and split it into a perfectly balanced combination of two possible paths. And you can see that you can see these two one linear lights into splitting into two linear lights, correct? But for the quantum sites, quantum energy, Hadamard gates, we are splitting the zero into a perfect superposition of 1 over square root 2, 0 plus 1 over square root 2, 1. So that means after passing the Hadamard gates, we can observe not only 0 as before, but we can observe 1 as well, but each with probability 1 over half. So now takes about 30 seconds and answer this problem with your partner. If 0 pass through the probability, 0 pass through the Hadamard gate, why do we not observe two light beams? Like, why do we not observe a 0 and 1 at the same time? Like two different answers for it. Because in beam splitter, when we pass through a light, we will observe from one light, we will split into two lights. So for this quantum side, why do we just observe one thing instead of two things? Yeah, exactly, because they are probability amplitudes, they are waves, and when we observe it, we will only observe one with one of the probability. So that is one key difference between the classical wave superposition and also the cubic superposition. And the difference is that we can only observe one thing after one outcome after passing through the Hadamard gate instead of observing two outcomes at the same time, like the optical beam splitter. So I'm going to close this lesson right now. So to close it, I'm going to ask you one question, and you are going to answer it in one sentence. How is the classical wave superposition different from the cubic superposition, and what are the similarities and differences? Yeah, the similarities is that they are represented by waves as well, and they have the constructive interference and destructive interference. However, their amplitudes can only be smaller than one. That is the difference. In classical waves, they can be arbitrarily tall and can be arbitrarily small. They can be way smaller than one. They can be way larger than one. But in quantum superposition, we have this constraint. And also, if alpha is big, beta has to be small. So the key takeaway is the physics 3, waves, oscillations, and amplitudes. This can be this knowledge can be brought forth to the quantum side. Even if when you're learning to quantum physics AP class, this knowledge can be extremely useful. And by knowing the similarities and differences, you can clearly distinguish between the two, and also how quantum physics is what was developed.